Hello friends, this will also be a short video about half an hour talking about uniform circular motion. In the previous lecture we talked about uniform circular motion and the properties of uniform circular motion. We said there is a constant linear velocity going along the circle and there's constant angular velocity spanning an angle, and the distance traveled per unit time is the linear velocity, and distance or angle spanned per unit time was angular velocity. We also talked about period and frequency. Period was the time it takes for one full motion to finish, and frequency was the number of motions per unit time, which is generally second. And we learned that period is equal to 1 over f, or f is equal to 1 over t, vice versa. The unit for period was second, generally used, and unit for frequency is second to minus 1, or also called hertz. We derived the equation for linear velocity to be 2 pi over t times r, or also omega times r, because omega was equal to 2 pi over t. And acceleration, which was what we call the centripetal acceleration directed towards the center, was equal to v squared over r. And force, centripetal force, if there's an acceleration in the same direction, there's also a force, and it's called centripetal force, also is equal to mv squared over r, coming from the fact that Newton's second law shows F is equal to ma, so m times this a. One thing I also want to show you about these equations now is that if v is equal to 2 pi r over t, and t is equal to 1 over f, this is also equal to 2 pi f. You can also use this, and the same goes for omega, angular velocity, 2 pi over t, 2 pi f times r, so in there 2 pi over t is also equal to 2 pi f. Also for the centripetal force, v squared over r, if we replace v by omega times r from here, let me put omega times r here, Fc can also be written as m times omega squared times r. So all these equations can be used depending on what we know. If we know t directly in the question, we can use this one, 2 pi r over t, as to find linear velocity. If we know f, we can use 2 pi r times f. And same goes for the other equations. We talk about the horizontal circular motion when we are rotating an object along horizontal. My keys didn't work well last time, so I decided to make a device for me to show you circular motion. It's the small earth I tied to a rope, and I'm going to show you with this one today. So if I rotate this on my head like this along horizontal, more or less, then I'm not interested in mg. Mg is maintained by airlift. I'm only interested in when I'm looking at tension in the rope, I'm only interested in Fc. And we solved a problem involving circular motion along horizontal. Let me remind you that, assume this is along horizontal only. I have a mass rotating around, and we said we always feel the centripetal force pushing us outward from the center. For easiness or simplicity, we'll be showing outward the center to understand the constant better. And if I look at the tension force along the rope, will be in opposite direction. If the rope is not breaking, the system is in equilibrium, so the tension force is either bigger or equal to Fc, otherwise it would break. This will help us to find tension force. If we are asked to find tension force, we know mass, velocity, and r. We can just equate it to Fc and say it's at least equal to Fc if it's safely rotating without breaking the rope, like in this situation. And assume this is perfectly horizontal. Today we're going to talk about vertical circular motion. Let me delete these extra equations I put in here. And we're looking at applications, and we're looking at vertical uniform circular motion today. And vertical motion will be, as the name suggests, along vertical. Now we are interested in the gravitational force acting on this object. In the bottom point of the circle, we have push down, increase in the tension. Up here, we have push decrease in the tension. So along the circular path, now the tension will be changing. And we'll calculate it using mg and Fc, centripetal force. So let's look at this in a way of example. We'll define at each point what is the tension along the rope. So assume we have a perfect vertical circular motion. And of course it is uniform. I am looking at the tension in the rope at these positions. What I will call as A, B, C, and D. What we're going to use is the equilibrium. Again, if the rope is not breaking, the tension force is at least equal to the forces pulling outside, or larger. We'll assume it is equal and solve for the tension. An object is doing a perfect vertical uniform circular motion. Along vertical plane. Define the tension force in the rope at points shown, points A, B, C, and D. Let's start with A. We have an object here, mg is pulling down, and also it's rotating, it has a velocity, so there will be a centripetal force pushing outside, mv squared over r. So we have Fc pushing down, and we have T, tension along the rope, let me call this TA, pulling out. So at point A, what we have, force is pulling down, Fc plus mg are equal to forces pulling us up, TA. TA will be equal to at least or larger than mg plus Fc in point A. If we have to find it, that's what we're going to use to find it. At point B, we still assume equilibrium. We have the mass in here. Now mass is downward in this point, maintained by airlift. We don't care about it anymore because it's not affecting the tension. Tension is towards the center, pulling the rope, acting on the object. Let's call this TB. And Fc, centripetal force outward. These two forces must be equal to each other if the system is in equilibrium. So at point B, what we have, force pushing to the right, Fc, is equal to force pulling to the left, TB. And that's all. Directly, if I jump to D and look at it, I will have a similar situation, only direction will be opposite. T is pulling, TD is pulling to right direction, Fc will be pushing outward, and I'm still not interested in mg. Now it does not have effect on the tension force, so at point D as well, we'll have the same situation. Point D, we'll have Fc is equal to TD. So TB, the tension force at B, is equal to tension force at T. Only different positions. At point C, we have mass pulling down mg, gravitational force. We have tension Tc pulling down, and we have Fc, centripetal force, pushing upward direction. If we again assume equilibrium, point C, force is pulling downward, Tc, tension force at rope at point C, plus mg is equal to Fc. Solving for Tc, what we'll have at point C is Fc minus mg. Using these values, using these ideas, we can solve for tension in the rope or some other questions. For this object to safely go from the up position here without falling down like this, the Fc should be pushing outward with a force at least equal to mg, because mg is pulling down, Fc is pushing outward, they should be at least equal so the object can go like this. Can Fc be larger? Yes. So the faster I rotate this, the safer it will pass from the upper position. Because Fc is pushing outward, mg is pulling downward. And if I want to calculate the tension in the rope, these are the equations I use. Same thing as in the equilibrium part in Newton's law section. Let me delete this now and let's solve numerical questions, calculating some things. The same situation goes for roller coasters, for example. Many of you, I'm sure, are fan of roller coasters, and there are points that are rotating like this, very scary points. So you are coming here, getting in there very fast, passing this point very fast, so that the circular motion will have the centripetal force pushing you upward. It is at least equal. Larger is better to total mg on the cart, all the people in the cart. So at this point, for safe passing condition, is Fc is at least equal or larger than mg. So if you're asked the question, if they are safely passing from this position, what is the velocity? We can use this to calculate what is the minimum velocity the cart should have for the people to pass from this position safely. Would be using Fc is equal to at least mg, and write down for Fc mv squared over r is equal to mg. We can solve for the minimum velocity for safe passage. Let's give these some values I showed and solve this, and then actually make this our example too. Let's say the mass, total mass in the cart is equal to 500 kilogram. Let's take it small. Let's not be logical, just take a value anyways. And the radius of the rotation you have in this roller coaster R is equal to 10 meters. Okay, so a roller coaster rotating around a circle which has a radius of 10 meters. If the mass of the cart with the people are equal to 5 kilogram, what is the minimum speed? Minimum speed for safe passing from the top of the roller coaster track. I have a very small board, unfortunately, but so we have a roller coaster, a car is going along the roller coaster. If the mass of the roller coaster is about 50 kilogram and the rotational circle has 10 meters radius, what is the minimum speed of the roller coaster for safe passage from the top of this roller coaster track? What we're going to do here is to use the same thing again. At least Fc should be equal to mg. So mv squared over r is equal to mg. And m actually can be cancelled here. We don't even have to take it into account. V squared should be at least equal to r times g. We can also put here bigger or equal. Bigger is safer. So v should be bigger or equal rg in square root. And let's put the values. We have 10 meters times 9.8 meters per second squared. So if we are rotating around the circle with 10 meters, regardless of the mass, because they cancel each other, at least our velocity should be that. For safe passage, 98, the square root of 98 will be our answer. Let me see that. I just came up with this question, so I know the answer. It's 9.48, 9.5, let's say, meters per second. 9.5 meters per second. Yes. So this is the safe passage. If r increases, then safe passage velocity should also be increasing. So this is for vertical motion. If we are asked here to find the normal force, for example, sometimes we have questions asking us to find normal force, the mg and fc will be given, and we'll be showing normal force exactly the same way as the rope, tension in the rope. It's the same thing. Normal force is always pushing against the surface perpendicular against the surface. Over here, for example, what we will have mg pulling down and fc pulling outward as well. Normal force will be pulling in the other direction, inward direction. Let's call this n. N will be equal to mg plus fc in here. Using equilibrium condition, downward pulling forces are equal to upward pushing forces. So it will be, n will be mg plus fc. If we know the values, we can calculate n. Over here, we'll do the same. N is outward from the surface again. mg plus n now is equal to fc, right? In this point, mg plus n is equal to fc. So n is equal to fc minus mg. If I know velocity, mass, and r, I can calculate normal force in here as well. But if I'm looking at the condition of safe pass, I'm going to say at least at this position, upper position, of my force of the centripetal force should be at least equal to mg. So for velocity, which will be r squared of rg always in this situation. Okay, let's delete this now. Now once we get into horizontal and vertical motions both involved, there could be motions with angle. For example, this motion would be a lot more complicated. We have tension here, and I am rotating this along horizontal. Now I have mg in effect to find the tension, and I have fc in effect. This will be quite complicated questions. I'm not planning to involve these type of questions, but I want to solve a question involving roads, slanted roads. So we have also in the class using learning calculators, first look at an example of what happens if the road does not have any angle. So a car is rotating. I think we talked about this in the previous lecture as well. Around horizontal turn, what should the friction or frictional force acting on the car? At least be in order to pass or turn safely. We solved a numerical question in class, but if we are turning around a perfectly horizontal without any incline of a road, if we have a car in here and it's rotating around this road, it will have, of course, a linear velocity. Sometimes omega is given. You can solve for fc using omega, and generally they have to give us the radius we are rotating around the road. So what will be pushing this car outward from the road will be fc, and what can only keep it in its place will be frictional force. Let me call it F kinetic. And for the car to safely turn around this bank, this road, kinetic frictional force should be at least equal to fc, or should be bigger. This will help us solve for kinetic frictional force. Sometimes they ask us about mu k as well. We know this is equal to, kinetic frictional force is equal to mu k times n, should be larger or equal to fc. Okay? Let's give these values and solve it. let's say mass is equal to 500 kilogram, R is equal to 20 meters. We solved a very similar question, and V is equal to 10 meters per second. What should mu k be at least for a safe turn? So we have Fc should be equal to Fk for a safe turn at least. Shouldn't be larger. But Fk could be larger. Using this, we can solve for mu k. So we say Fk is equal to Fc. Mu k times n is equal to m v squared over r. And n in here, we only have mass pushing on the road. And normal force will be outside of the road and will be equal to mg. So mu k, n is now equal to mg here. It's very hard to draw it. It will be out of the board. But n is equal to here, mg. So mu k times m times g will be equal to m v squared over r. Either you can enter the m value, but you may just again cancel it in here and solve for mu k. So over here, mu k will be equal to v squared over r g. And let's solve for it actually. So v is 10, v squared is 100 divided by 9.8 times r, 20 meters. 0.5. So our mu k should be at least 0.5 for this car to rotate around this turn safely. Could it be larger? Yes. If it's larger, even more safer. Here is the minimum equilibrium position. Fk should be equal to Fc. If it's larger, better. But generally, to solve questions, we equate them to each other. Now, some more complicated questions could include incline as the car turns, which is a more general, more realistic situation. Generally, we would have an inclined road, and they make the road inclined to actually increase the safety of the turns. Perfect horizontal roads are not as safe. So let's look at a situation like this. And again, if you have any questions, we have a perfect horizontal turn question. We'll also solve the inclined question in class. So you should be able to understand everything, hopefully. I have a question here with the inclined road. Let's solve this, and it's about 30 minutes. I think we'll stop after this. 22 minutes, one more question will be good enough. Let me draw the figure first. My example is 3, 4. There's a nice figure here. I'm not sure if I can draw as nice, but let me try. So we have a road in here. A racetrack with an incline. We have an angle in here. And a car is going along this road. Okay. Lightning McQueen. My son keeps watching this movie, so I remember that. So this circle will have a radius r, and car have a mass. And let me read you the question. The Daytona 500 is the major event of NASCAR, National Association for Stock Car Early Racing Season. It is held at Daytona International Speedway in Daytona. Extra information. The turns in this oval track have a maximum radius of 316 meters. So R is equal to 316 meters. And are banked steeply with angle theta 31 degrees. So theta is equal to 31 degrees. Suppose these maximum radius turns were frictionless, so we assume there's no friction in here. At what speed would the cars have to travel around them for safely turn? So what should the speed be for a safe turn in this situation? And the track is frictionless, so we don't have to care about friction. Let me draw the figure here largely and show only the car along the steep inclined road. We have a 31-degree angle, and the car is our mass, right? And it's rotating around this circle, right? And let's draw the forces in here. We will have mg, and we have an incline. We are pretty comfortable with incline now, I hope. But along the incline, what I will have is mg sine 31. That's always the case. And perpendicular to incline, what I have is mg cosine 31. I'm not really interested in this one here because there's no friction. If there was friction, it would be important, but in this question it won't be. I just wanted to show you to remind you. So delete this. We don't worry about that. No friction, no normal forces are of interest. We have another force pushing outward in here. This is interesting. Centripetal force in this direction. Now using these angles, I can solve for centripetal force. Let me draw that. This will be 31 degree. This is 90 degrees, so this is 90 minus 31. Let me see if I have it in there. Now let's find it out. 90 minus 31. 90 minus 30 is 60, right? So 59. It should be. This angle is 59 degree. If I set my usually chosen XY coordinate system in here, along I'll have X, perpendicular to incline I'll have Y. This FC will have a component along X. If this is 31, this is 59, this will also be 31. So this angle will always be equal to that angle. This could be a very complicated question you can have. The most complicated I would ask you would be this. Don't worry too much about it, but it's a very nice question. So we will have FC, will have a component along X in here. FCX, centripetal force, X component of centripetal force, trying to push the car outward, and mg sine 31 will be pushing inward. And since this is 31, this is also 31, if you look at XY coordinate system, FCX will be FC cosine 31. Next time we don't even have to go to 59 in here because we know these two angles are always equal to each other. So for the equilibrium, the safe turn, at least mg sine 31 should be equal to fc cosine 31. And I know we have velocity, we have r, let's put everything in place. Mg sine 31 is equal to, I'm putting value for fcm, we squared over r cosine 31. Let's cancel m's and solve for v. Leaving v alone in here, we will have v squared is equal to r comes as multiplication, r g sine 31, and cosine comes as division, cosine 31. V squared is equal to rg, sine over cosine is tangent 31. So v is equal to square root of rg tangent 31. And we can solve for this. We know r, 316 times g, 9.8 times tangent 31. From here, you should find v as, let me see my answers, 43.1 meters per second. So what we did is find the component of mg pulling inward and component of fc pulling outward. They at least should be equal to each other, or mg sine 30 should be larger than fcx for the safe turn. Using the equality, we solve for at least the velocity, the minimum velocity the car should have for a safe turn. If it is larger than this, it will not turn safely. One more thing I want to show you, it's very interesting. So we have talked about this object, vertical motion passing from the upward position. For it to safely pass, at least FC should be equal to mg in here, so it will not fall down. Same goes for the motorcycle driver, same goes for the roller coaster. When people are passing from the upper part, they should have large enough velocity to make FC, centripetal force, large enough, pushing outward, so it will be larger than mg. The objects will not fall. There's a very interesting experiment for a bucket of water. It's actually an example in here. Let me find it if I can. And solve it, and we're out of here. So last question today. Example 5, I think. We have a figure showing a bucket of water. So we have a circle. And we have water tied to a rope in a bucket. So, and we're rotating this bucket of water. Okay. It will be coming to upward position, of course, at some time. And can there be any situation we can rotate this bucket of water without spilling the water? That's the question. If r is equal to 1 meter, what should the period of rotation be? What should the period of rotation be that the water will stay in the bucket for sure? That the water will stay in the bucket. For sure. So for this to happen, if I can safely pass the highest position, the other positions will also be fine. And this depends on period, frequency, of course, because velocity depends on these. So let's write down first what we know. We have at highest position, I say I'll consider this highest position because if I can maintain a motion where at this highest, most dangerous position, Fc is equal to mg or larger than mg, water will be passing from there without spilling. If it's larger, it's going to be even safer. And how can I make this happen for sure? So at the highest point, oh, 33 will be good. Highest point, then we say Fc should be larger or at least equal to mg, right? But I want to make it for safety, not to spill my bucket of water, larger. So let me calculate what it should be at least. Equal situation to decide that. Fc, so we will have, this bucket of water is rotating, we'll have velocity in here, and v squared over r should be at least equal to mg. Regardless of the mass, I can cancel the mass, I can calculate the smallest velocity I should have, the bucket should have for safe turn. And it should be v squared is equal to square root of rg, v is equal to v squared is equal to rg, sorry, v is equal to square root of rg. Now r is 1 meter, we put in here, MKS units, and g is 9.8 meters per second squared. So our velocity should be square root of 9.8, so let's find that. 3.13 Now it can ask me about frequency, or it can ask me about period. I don't care because I know what V is equal to. V is equal to 2 pi over T times R, or 2 pi RF. I didn't put it in here. It's also equal to 2 pi RF because F is equal to 1 over T. So they're asking me about T. Let me solve it in here. If I know V, I can get to T. My V should be, let me open my light first. I have a very interesting room. V is equal to 2 pi R over T, so I can solve for T in here. T is equal to 2 pi R over V. 2 pi 1 meters divided by T.13 meters per second. Let's solve for that, or do I have a solution already? 1.9 seconds. So if I have a bucket of water, I don't have enough space in here, but we're going to do it in the class, so we're going to try this. We have a bucket of water here. If I rotate this with a frequency, this is about half a meter. So if R is smaller, my period should be larger, will be smaller as well, so I'm safer actually if it's shorter. So for one turn I should take less time if I have less. Yeah, it's not a 1 meter. If I can turn it fast enough, if I'm fast enough, my T will be small, right? V and T are inversely proportional. I should be able to safely rotate this bucket of water, and we'll try it in class. It should work. So I'll try to rotate it as fast as possible to be able to pass this point quickly. If we think about frequency, the period should be small, frequency should be large. So in 1 second, I should be able to rotate it as many times as possible for safe turn from this top point. If it's safe return from here, here, all will be fine. This is the most dangerous position, and we calculated how it should pass from there. So we'll try this in class. See you on Wednesday.